Good afternoon everybody. Today I am going to tell you about a very important thermodynamic function, which is called thermodynamic free energy function. Now you must have studied this free energy several times in your previous classes also, but today I am going to give you a detailed picture of it. So as we all know that thermodynamic free energy function is of two types: Helmholtz free energy function, which is also known as the work function, and it is denoted by A. And the another one is the Gibbs free energy function, which is denoted by G. Now let us suppose this is a thermodynamic system. Now in this thermodynamic system, suppose Q is the amount of heat that is being absorbed by the system for doing the work, and at temperature T, and S is the entropy of the system. So this is a thermodynamic system in which Q is the amount of heat that is being absorbed at temperature T, and S is the entropy of the system. Now we all know that the unavailable energy, means the energy which is required for the system to be updated, is Q. So is T into S. The unavailable energy which must be kept in the system is the product of the temperature and the entropy, which is T into S. This. What heat is being supplied to the system? That is Q. And the entropy is S. And the unavailable energy is the product of temperature and the entropy. And that is T into S. So what will be the available energy? The available energy which can be utilized to do the work. That is Q minus Ts. Because Q is the energy supplied. Ts is the energy which is unavailable energy is required to maintain the system. So the available energy will be the difference of the supplied energy and the unavailable energy, which is equal to Q minus Ts. Now when we study a system at constant temperature and constant volume, then the free energy, the energy which is available to do the work, is given by the Helmholtz free energy or the work function. It is denoted by A, and in several books it may be denoted by F also. And the energy, available energy to do the work, which is obtained when the system is maintained at constant temperature and constant pressure. Then we have this Gibbs free energy G. One thing I have to tell you here, that this is actually since the system is maintained at constant volume, then this Q will be E. I will explain this to you later on. So actually the work function A is defined by the E minus Ts. The work function A is defined by E minus Ts, and the conditions maintained are constant temperature and constant volume. That is isothermal process and isochoric process. Whereas in the Gibbs free energy, it is maintained at constant pressure, isothermal process and isobaric process, and here we define G by H minus Ts. H, as we all know, is enthalpy of the system. At constant pressures, we usually use this heat content H. So this is G is equal to H minus Ts. G is the free energy, so it is the difference of H and the product of the entropy and the S. So this is the Gibbs free energy, and this is the Helmholtz free energy, which is also known as the work function, denoted by A or F. In German, A stands for Arbeit and Arbeit stands for work. So this is A is equal to E minus Ts, and we have here G is equal to H minus Ts. Moreover, both these free energy functions, they are state functions and they are extensive properties. State functions, as you all know, that the state functions depend only on the initial state and the final state. So they both are state functions, and since this E, this S and here H, all the quantities which are used to define it, they are also state functions. So both the free energy functions, both the thermodynamic free energy functions, the Helmholtz free energy function and the Gibbs free energy function, they both are state functions, and moreover they are extensive properties also. And now I will tell you about in detail about variation of Helmholtz free energy and also the Gibbs free energy, and what is their physical significance. So now I will tell you about the physical significance of A means the work function, and later on I will tell you about the physical significance of Gibbs free energy. What do they denote actually? About the work function and its physical significance. So from first law of thermodynamics, we all know that the heat supplied to the system is used in partly in increasing the internal energy of the system and in doing the external work. Now in this case, as we have seen that it is carried out at a constant temperature and a constant volume, then suppose this is the expression for first law of thermodynamics. You all know that Q, the heat supplied, is equal to E plus PdV. Here dV is the change in volume and PdV is the product of the change in volume. The pressure is the work done, as we all know. So this dV is equal to 0 here because the process is isochromatic. So this Q is equal to E. Since dV is 0, so the product of P and dV will be 0. So this Q will be equal to E. And here we arrive at the Helmholtz work function. So A will be equal to E minus Ts. As we all know that what was the available energy was Q minus Ts. I just told you that it was Q minus Ts. And here Q will be replaced by E. Why? Because it is an isochoric process, means the volume is constant. Volume is constant means dV is constant. And when dV is constant, then from first law of thermodynamics, Q will be equal to E, and this A is equal to E minus Ts. This is the energy which is available to do the work in a system. So A is equal to E minus Ts. So now we come on to the physical significance of this work function A. Suppose we take the initial and the final state. As we all know, it is a state function, and in the initial state, let it be for an isothermal change that A1 is equal to E1 minus Ts1. 1 is the initial state, and A2 is equal to E2 minus Ts2. By 2 we denote the final state. Let it be equation number 1 and let it be equation number 2. Now if we subtract them to find the change in the free energy, let us subtract 2 and 1. What we finally get is A2 minus A1 is equal to E2 minus D1 minus T S2 minus S1. This is a simple mathematical step, and delta A will be equivalent to delta E minus D delta S. Let it be equation number 1, 2, 3 and 4. Now we all know from first law of thermodynamics that Q is equal to the heat absorbed is equal to the change in the internal energy plus the work done in the system. So delta E is simple rearrangement here. Delta E is equal to Q reversible minus delta S. Let it be equation number 5. Now we have also studied the second law of thermodynamics, from which we got the entropy. So this change in entropy is equal to the heat absorbed for the reversible process divided by the temperature at which that heat is being absorbed. So Q reversible, a simple rearrangement here also. So Q reversible will be equal to T into delta S, T into delta S. Here comes equation number 6. Now we are having this equation number 4, which has delta A is equal to delta E minus T delta S. Now from that equation, where we have derived from the first law of thermodynamics, we have that the change in internal energy delta E is equal to Q reversible minus W/X. Let us substitute delta E for Q reversible minus W/X in equation number 4. Similarly, let us substitute the value of Q reversible T delta S in equation number 4. What we get? Delta A is equal to T reversible minus W/X minus Q reversible. T delta S from second law of thermodynamics is equivalent to Q reversible. We get equation number 7 here. Now let's look at equation number 7. What we have? This Q reversible, this will get cancelled, and what is remaining is minus W/X. So delta A, the change in the work function, is equal to minus W/X. Or we can write it in this way also, that minus delta A means the decrease in the free energy function, Helmholtz free energy function or work function, is equal to how much? W/X. So finally, from equation number 9 we can see that the maximum amount of useful non-PV work that can be obtained from a system is also known as the work function. The conditions maintained are the constant temperature and the constant volume. Now, I will tell you about the Helmholtz function, about the Gibbs function, which is denoted by G. The physical significance of it and what is the difference between that. Now I will tell you about the physical significance of Gibbs free energy, which is denoted by G. So I will tell you about the physical significance of Gibbs free energy G. G is defined by H minus Ts. In a similar way, like we have done for the initial and final states for the Helmholtz free energy function. In a similar way, we have arrived at this change in the free energy. I am not repeating it because I have just now done it for the Helmholtz free energy function. So this delta G, which is the change in the free energy, is equal to delta H minus T delta S. At constant temperature, since this process is taking, we are calculating it at constant temperature. So the expression for the change in the Gibbs free energy will be delta G is equal to delta H minus T delta S, and it's very easy to arrive at this equation from considering the initial state and the final state and the difference between them. So delta G is equal to delta H minus T delta S. Let it be equation number 1 and let this be the equation number 2. Now, as we all know that the change in enthalpy is actually equal to delta E plus P delta V. P delta V is the work done, the product of the pressure and the volume, change in the volume. So delta H is equal to delta E plus P delta V. Let us substitute this value of delta H in this equation number 2. What we get? Delta H is equal to delta E plus P delta V minus T delta S. We have simply substituted the value of delta H, which is delta E plus P delta V, from this equation number 3 in equation number 2. It's very simple to understand. So delta G will be delta E plus P delta V minus T delta S. And we have finally equation number 4. Now just see, delta G will be equal to, a slight rearrangement is there. I have brought it to this place and this I have shifted to this just for your understanding. So delta E minus T delta S plus P delta. This is the same equation, both are same equation, equation number 4 and 5 are same, except that a little bit rearrangement has been done just for your understanding. So delta G will be equal, now this delta G minus T delta S, we have just now studied that it is the work function, the Helmholtz free energy, the work function, and which is denoted by delta A. So delta G will be equal to, this is delta A, this is delta A plus P delta V, and here we have the P delta. So what we have, the change in free energy is the sum of delta A, the change in the Helmholtz free energy, and the work done P delta V. So now if we are here to calculate the decrease in the free energy, what we do is simply the minus sign here. This is only for the calculations, for understanding, because minus delta G will now signify the decrease in the free energy. So minus delta G will be equal to negative of delta A and negative of the P delta V. We have the equation number 6. So minus delta G, the change in free energy, the decrease in the free energy will be, this is what W max. We have just now seen that the decrease in the Helmholtz free energy or the decrease in the work function is equal to the maximum work that can be obtainable from the system minus P delta. So this we finally have it as the decrease in the free energy is equal to the difference of the maximum work that can be obtained and the work of expansion that is being done by the system. So this equation number 7 gives us the decrease in the free energy at constant temperature and constant pressure. The two conditions are constant temperature and constant pressure. So the decrease in free energy is given by the difference of the maximum work that can be obtained from the system and the work of expansion. So in a way we can say that the decrease in free energy for a process which is undergoing expansion, we can say at constant temperature and constant pressure is given by the work that can be obtained, total work that can be obtained minus the work of expansion done by the gas. Now there is a simple difference between the two types of free energies which you have just seen, the Helmholtz free energy and the Gibbs free energy. The main difference between them is that the Helmholtz free energy is carried out at constant temperature and constant volume, whereas the Gibbs free energy is at constant temperature and constant pressure. Moreover, both are extensive properties and both are state functions. So that's the main difference between them, that they are carried out at different pressures and moreover, where delta A is that the change in the free energy in the work function, change in the free energy work function is given by the maximum work done that can be obtained from the system. This change in the Gibbs energy signifies the net work that can be done, means the work which is other than the work of expansion, that is given by the decrease in the free energy. Moreover, this decrease in free energy has a wide applicability in determining the feasibility of a reaction, means whether a reaction is spontaneous or not, whether a reaction will occur or not occur. As you all know that there are certain criteria that whether a reaction will occur or not, like enthalpy is considered, like a process is exothermic or a process is endothermic. That also determines the heat, the spontaneity of a reaction in many processes. We can say that the reactions which give out heat, means which are exothermic, are spontaneous processes, but we can't say that because many processes where heat is taken in, those processes are spontaneous. So this is not a 100% sure criteria for determining the feasibility of a reaction. Moreover, the other thing we can say is that entropy change is criteria for the spontaneity of a reaction, means that the reaction will be feasible if the entropy is increasing. But there are so many processes where entropy decreases, still the reactions are feasible. Now comes into play the Gibbs free energy, the change in the Gibbs free energy, the decrease in the Gibbs free energy. The processes where there is decrease in the Gibbs free energy, that will be 100% spontaneous. So out of the three factors, we can say that this Gibbs free energy function is a very strong criterion for determining the spontaneity of the reaction, or determining whether a reaction will be feasible or not, whether a process will be feasible or not, whether a process will occur or not. Thank you.